Okay, welcome back. This is our fourth and last pre-recorded lecture for chapter 12. So I do hope that you are joining me in our synchronized sessions where we're actually going through problem solving. And here's sort of what we're going to cover today is we want to understand the effects of an electrolyte on colligative properties. So up to this point, we've looked at non-electrolytes, covalent molecules, and now we're going to look at electrolytes. I'm going to introduce a term called the Van Hoff factor, which deals with electrolytes. We're going to look at some more of those colligative properties. So we looked at vapor pressure in part 3. Now we're going to examine freezing point and boiling point, as well as osmotic pressure. So those are the other 3 colligative properties that we're going to look at in this chapter. And we're going to talk a little bit about ion pairing and what that does to your Van Hoff factor. So that might sound a little bit strange right now, but hopefully by the end of this pre-recorded lecture, you'll feel a little bit more comfortable with these terms. So let's start and talk about what is an electrolyte. So you guys remember from way back when, an electrolyte versus a non-electrolyte. And what an electrolyte is defined as a substance that produces ions in solution. And so we typically think of these things as salts. So salt is sort of our generic term for an ionic compound. So NaCl, magnesium fluoride, maybe calcium chloride. Okay, those would be examples of a salt. Calcium nitrate, those would all be salts. So ionic compounds, our generic term for that is a salt. And also acids. Right, acids that dissociate. So hydrochloric acid, for instance, would form hydrogen ion and chloride ion. So that's a substance that's going to produce ions in solutions. So these would all be electrolytes. A non-electrolyte is your covalent compounds. So these are substances that do not produce, obviously, ions in solution. So these are your covalent molecules. So things like glucose, sugar, methanol, those are 2 solids that we talked about in part 3. These would be non-electrolytes because they're not going to break apart. So 1 particle of glucose is 1 particle in solution. So if we think about colligative properties, remember, only depend on the amount or the number of particles, not the type. So electrolytes and non-electrolytes are going to be different because if I have 1 mole of glucose, say, and I add that to solution, to a solvent, then I'm going to have 1 mole of glucose in solution. If I have 1 mole of NaCl and I add that to a solvent, in this case maybe water, then I'm going to have 1 mole of sodium ions and 1 mole of chloride ions in solution. And so if for colligative property it only depends on the amount of particles, this is going to have 2 times the effect, because 1 mole of this produces 2 moles of particles. So I would expect this to have a greater effect on those colligative properties than glucose, because 1 mole of glucose is going to produce 1 mole of glucose in solution. But if I have an electrolyte now, I have to look at the number of ions that that's producing in solution. 1 mole of, say, magnesium fluoride, and I add that to solvent. Now I'm going to produce 1 mole of magnesium ions and 2 moles of fluoride ions in solution. So now I have created a solution where I have 3 moles of particles. So this is going to have an even greater effect on a colligative property than sodium chloride, because now I have 3 particles in solution, 3 moles of particles, where here I would have 2 moles of particles and here I have 1 mole of particle. So distinguishing between an electrolyte and a non-electrolyte is going to be really important in colligative properties, where it only matters how many of them are there. The thing that allows us to do that is this guy called the Van Hoff factor. It sounds very German. That is I. And I is going to be number of moles of particles in solution over the number of moles of formula units dissolved. So remember, NaCl, this would be the formula unit. It's also the chemical formula, it's also the empirical formula. So ionic compounds are special in that we write them as the empirical formula, the lowest whole number ratio. We call that the formula unit. So my Van Hoff factor would be the number of moles of particles in solution divided by the number of moles of formula units dissolved. So the assumption is this is always going to be 1. So if I take one of these, I'm going to make 2 moles of particles. So I, for NaCl, I would expect I to be 2 moles because I have 1 mole of Na and 1 mole of Cl divided by 1 mole of NaCl. That's my formula unit. So I would expect that Van Hoff factor to be 2. Now we're going to come back to this idea, the Van Hoff factor, here in a second. So now we're going to look at 2 colligative properties. We're going to assume right now that we're dealing with non-electrolytes, and then we'll come back and look at electrolytes. Okay, so we're going to look at non-electrolytes. So these are going to be covalent molecules in solution as my solute. And I'm going to consider temperature point. So I'm going to look at freezing point and boiling point, and also osmotic pressure. We'll come back to osmotic pressure. So let's look at freezing point and boiling point. If I have a solution in a solution where I've added, because this is a colligative property, I'm going to lower the freezing point of the solvent. In colligative properties, we're always looking at what the majority component is. So in this case, the majority component of a solution is always the solvent. So if I make a solution, what I'm doing is I'm lowering the freezing point of that solvent. Think about icing roads in the winter, right? We don't really have that here in California, but icing roads in the winter, we salt the roads because what that does is that lowers the freezing point of water, and it takes water from being ice back to water in the liquid phase. And then our cars will drive much better on that. In a solution here, for boiling point, I'm going to elevate, or I'm going to increase the boiling point of the solvent by adding my solute here. Osmotic pressure, we'll come back to osmotic pressure. So let's look at freezing point and boiling point, because these have very similar equations. These are going to have a change in temperature, right? I'm either increasing or I'm decreasing the temperature. Change in temperature is going to equal to the number of particles. And since I have a solution here, I'm going to define that as the molality. So if you remember cursive M, this is my molality of my solution. So the concentration of that solution in terms of molality. This is really the only time we use molality as a concentration unit. And remember, this is moles of solute over kilograms of solvent. So that's my molality. I have solute over solvent. And then the final thing is I'm going to have a constant here. And this is the constant that deals with the solution. So this is a constant that is unique to the solvent and also unique to boiling point or freezing point. Okay, so I'm going to have a different constant for each one. This is going to be the change in temperature in units of degrees Celsius to the solvent's freezing point or boiling point. Okay, so I'm changing the solvent's freezing point or boiling point by adding in my solute. I'm going to keep track of how much of that solute is there by looking at the molality of the solution, and then this is going to be a constant. So let's apply it first to freezing point. And I'm going to look up these values in a table. Actually, let me show you the table first. Here, I'll move this back down. So this table is in your textbook, and it looks like this. And so what you see here is this table is going to be based on the solvent. Colligative properties, we're concerned about what's happening with the solvent. Here you see I have a solvent of benzene, carbon tetrachloride, I have chloroform, and all the way down at the bottom I have water. And so here's the normal freezing point of that solvent, and this would be that constant. So the little f means that that's going to be my freezing point constant. So this would be a freezing point. So I would use these two together. And then boiling point, so water freezes at 0 degrees Celsius, it boils at 100 degrees Celsius. This is my boiling point elevation constant here for water. And so you'll notice the units here. So this is the first time where you're actually able to do calculations. Well, actually not the first time, but this is one of the few times we're actually able to do calculations where you don't have to change temperature to Kelvin. I'm keeping temperature in Celsius. I'm actually going to do 2 problems with you in our lecture today. Okay, so we're looking at freezing point first. So I'm going to look up in the table and I'm going to get my value for freezing point. So we call this freezing point depression. Not that it's depressed, but I'm lowering it. So this means that I'm going to lower the freezing point of my solution by adding solute to it. That equation looks like this. My change in temperature, this is my change in temperature of my freezing point. I could just give it a little, I could maybe just give that an F here, equals my molality of my solution times my constant for my solvent, my constant for the freezing point of my solvent. Let's assume that I have my solvent is water. So the freezing point for water is 0 degrees Celsius. Water freezes at 0 degrees Celsius. If I look up the constant for water, that's 1.86 degrees Celsius in units of degrees Celsius per molality. So this is going to allow me to effectively cancel out my units of molality here. And let's say I have a solution that is 0.500 molality glucose. So I have a covalent compound. This is my concentration of my solution. I'm just going to plug this in here. 0.500 molality times 1.86 degrees Celsius per molality. And that's going to give me 0.93 degrees Celsius. So I'm going to take, this is the change in temperature. So that's what this is. And the freezing point of water is normally at 0 degrees Celsius, and I'm lowering the freezing point. So I'm going to take this and I'm going to subtract it. So my new freezing point for water is going to be 0 degrees Celsius minus 0.93 degrees Celsius. So it's going to now freeze at 0.93 degrees Celsius. So I've lowered the freezing point of water. So that would be freezing point depression. So that's one colligative property. So now I'm going to look at boiling point. And boiling point is going to look very similar. The only thing that's going to change is now I'm increasing the boiling point. So I'm adding to the boiling point of my solvent. And my constant is going to change. Boiling point elevation. So I'm increasing the boiling point of my solvent. I'm increasing the boiling point of solvent. That equation looks like this. So maybe we'll give this a B. Molality times that constant, but now that constant is going to be different because it's associated with the boiling point. So let's say I have my solvent is water again. Water has a boiling point of 100 degrees Celsius, so water will boil at 100 degrees Celsius. The constant for water is 0.512 degrees Celsius over molality. Now this is different, so my constants here are going to be different depending upon whether I'm looking at boiling point or freezing point. And boiling point is usually less. You're going to have less of an effect. Say my solution is a 0.5 molality glucose solution, and I want to know what is the new boiling point. So I'm just going to plug everything in. So my change in temperature is the molality of the solution times my constant here, and that's going to give me a value of 0.256 degrees Celsius. So that means my new boiling point for water is 100 degrees, because that's where it would normally boil, plus what it's being elevated. So now it's going to boil at 100.256 degrees Celsius. So that would be my new boiling point for water. So boiling point elevation, freezing point depression. Now the third thing we want to talk about is osmotic pressure. And osmotic pressure is also a colligative property. So osmotic pressure is simply the flow of solvent. So we're a colligative property. We're really looking at what's going on with that solvent, the majority component, from a solution of higher concentration to lower concentration. This is called not osmotic pressure, but this is really called osmosis. So osmosis is this flow from a higher concentration to a lower concentration. There's these things called osmosis cells, and I'll pull up a slide here really quickly to show you. And an osmosis cell is a enclosed environment, and it has this semi-permeable membrane, which allows a substance to pass through in only one direction. Osmotic pressure is what happens in this cell. It's a pressure that you can apply that is going to stop. So this is the pressure required to stop osmosis. So how much pressure do I need to apply to stop the osmosis in that osmotic cell? So let me show you what this cell looks like. This is an osmotic cell. If I were to just let this thing happen, so I have this side is my more concentrated solution. You can see I have more solute particles here. This is just my pure solvent. So over time, if I have this membrane here and I'm not doing anything with it, over time, solvent molecules are going to flow from this direction over into here. So I'm going to go from this lower concentration. So if I have this osmosis cell, what I'll see is the side that has the pure solvent, that's going to go down. It's going to push this side up because more solvent molecules are going into this higher concentration. So that difference, that change in volume, is the osmotic pressure. If I had a pressure to push down, this would be the pressure I would have to apply to keep this osmosis from happening. So it's a little kind of setup that's really hard to imagine, just because you've never seen one. You can't like touch it and feel it and oh, okay, I see what's happening here. But if you think about your body, so why can't you drink salt water? You're stranded in the middle of the ocean, you're in a little life vest, you're surrounded by water, and you're slowly dying because you need water in your body. If you were to drink the salt water, now you have a really high concentration of salt in your stomach and in your small intestines. And your small intestines are where you have a lot of nutrient exchange with your blood. And so there's a lot of availability of osmosis to be happening between the intestines and the blood flow. So you have these like they're kind of like semi-permeable membranes. If you have a really high concentration of salt in your intestines, what that's going to do is it's going to pull water from your blood, and basically it dehydrates you even more because you're pulling water from your blood, and so you're removing water from your body as opposed to what you think is you're drinking water. You should be putting water in. Osmotic pressure is the reason that happens. It has a very simple but weird looking formula. Here, osmotic pressure, that's what this pi is here. So we're going to define pi as that pressure, and it's going to have units of atmosphere because it's a pressure. So units of atmospheres. It's going to be equal to big M, which is molarity. So that's your concentration of your solution in units of moles per liter. R is the ideal gas constant, and T is the temperature in the form of Kelvin. And so that equation looks like this. Okay, so we've talked about freezing point depression, boiling point elevation, osmotic pressure. What we've been looking at are non-electrolyte solutions. So where you have 1 mole of your solute is going to dissolve into 1 mole of particles. And so remember our Van Hoff factor I. So I is going to account for an electrolyte. And so I'm going to add it to those equations. For a covalent compound, I is equal to 1. So even if I leave I into those equations, it's still going to give me the same value. So if I look at those 3 equations with I added in, this is what they look like. So this is how we're going to account for electrolyte solutions. I'm going to have my number of moles of particles, and I'm just going to multiply it by the molality and my constant. I'm going to multiply it by the molality and my constant. I'm going to multiply it by the molarity, R and T. And so I here, the only adjustment I'm going to make for an electrolyte is I'm just going to add I into those equations. Here, I is that Van Hoff factor, and it's the moles of particles over the moles of formula units dissolved. And so if we look at a solution, and we said NaCl, right? NaCl will divide into 2 moles of ions for every 1 mole of NaCl. That might look like this, where I have chlorine ions here and sodium ions here. What can happen in solution is this ion pairing. As you increase the number of ions in solution, you have the opportunity for these ions to actually pair together. And what happens is this Na and Cl here kind of kick out all these water molecules, and they reform into a formula unit, but they're so small that you don't really see it. So if I see sodium chloride in solution, that's thousands of ions that are in that solid phase together. But I can have these ion pairings and it still look like a solution. And so you have a little bit of this happening. The more ions you have in solution, so the greater the molarity or the molality of your solution, then the more opportunity you have for these ion pairings to happen. If you were to look at, say, let's just define a solution like 0.05 molality here. What you see is that a non-electrolyte is not going to have, it's still going to be 1 because it hasn't broken up into particles. But what you start to see is that your I that you would predict based on the number of ions in that formula is going to be a little bit lower than what you actually see. And that's as I get more ions in solution, as those ions have more of a charge, then there's going to be more opportunity to form those ion pairings. And so your I measured might be slightly less. For our calculations, we're going to assume that we don't have ion pairing. And so for NaCl, this would be a 2. I would just multiply everything by 2. For magnesium fluoride, I would just multiply everything by 3. But just know if you're solving for I, you could have a value that's going to be less than what you predict because you're going to have ion pairing. And so some of our calculations, we might be solving for I, and then I is going to be a little bit less than what we would expect. If you're not given those values and you're just using these equations, then you would just use the I that you would predict based on the chemical formula for that. So this kind of ends the whole chapter. So just to give you a reminder of all the things that we've covered in this chapter, the equations that we've covered is Henry's law. That's the solubility of gases, right? So looking at the molarity of a gas in solution. Raoult's law, now we're dealing in colligative properties, so vapor pressure, osmotic pressure, we had freezing point elevation, freezing point depression, and then we looked at those heats of hydration, so that ionic equation itself. What I also have online for you guys, and I'm just going to go back to my sheet here, is I've put together these equation quick sheets for you, and these are PDFs, and I'm going to do one for each chapter, and these just have a summary of all the concepts, the equations that we've covered that you might need or find handy when you're doing calculations. And so this is just what chapter 12 looks like. So this was what we did in part 1, and part 2 was these heats of solution. We covered concentration in part 2 and part 3, and then part 4, which we've been doing today, is vapor pressure and these colligative properties, right? So vapor pressure we did in part 3, and then we looked at the rest of these colligative properties today. This equation sheet might be handy to have, to print out and have available when you're working through those problems as well. Okay. So this will end our chapter 12 sort of formal pre-recorded lectures, and then I'll look forward to seeing you guys in our Zoom sessions where we work through problems.